Hello and welcome to another overview video for the differential equations class, our last one, module 10, where we look at sort of introduction to systems of differential equations. Here's an example of a system of differential equations. This is one form of the uh, somewhat well-known Navier-Stokes equations. Now what you have here are partial differential equations, indicated by the partial derivative operators and the subscripts. You also have three equations, and in general, it could be any kind of differential equations and any number, um, and you just have to have derivatives and equations, and then the connection between them. Um, as an introductory class, have been focusing on ordinary differential equations, and so this will be the same thing. We're also going to restrict these to linear differential equations and first order differential equations. So if you do restrict to first order linear systems of ordinary differential equations, then the general form is shown here. Now this has n equations and then n unknown functions. And then y is used for all of them, and then you just do a subscript. So y1 is the first function, y2 the second function, and then yn is the last function. And then you have your forcing functions also subscripted. Independent variable is t here. And in general, this can be represented more in terms of linear algebra, where the solution y is actually a vector, and the components of that vector are the y's. And this is still pretty challenging, so we're going to restrict it even further to about as simple as it can get, right? If you just have one equation, it's not a system. So we're going to have two equations, two unknown functions, y1 and y2. Linear first order, we're going to make it homogeneous, so the forcing functions are gone. And then we're going to use constant coefficients for the coefficient functions. So here's an example of the kind of problem we'd like to solve, the first step in solving a system of ODEs. And it may be represented this way right now in the terms of the two equations, but you pretty much have to deal with some linear algebra notation here. And so here's the equivalent matrix representation. And here they're using the vectors for y and y prime. So the vector y, which it's in the textbooks like ours, the Trench book will use sort of a bold font to indicate a vector. When you're doing handwriting, you can't really do bold font. So I think you recommend using the little arrow to indicate that it is indeed a vector. And then I like using the square brackets and writing these as column vectors. So the vector y has first component y1 and second component y2. So then you can think of that as the solution in vector form, or you can think of it as being two separate scalar functions that comprise the solution. In the same way, this is a vector y prime, and it has components y1 prime and y2 prime. And of course, when you multiply these out, so we've got -4, -3, 6, 5. So on the right side, this is the matrix multiplying to a vector. And you would take the first row and then do the dot product with that column. So you get -4 times y1, and then -3 times y2, right? And then that matches up with that. And in the second row, you would do the dot product with the second row, and then the same column. So if you're new to working with matrices, it's good to expand these things out and get more comfortable with Uh, though it seems like in a lot of the examples, they'll start with the expanded separate equations, and then we'll go to the matrix form for doing the later calculations. And then this matrix that comprises the constant coefficients is often denoted with A. And they just use the capital letters for the matrix, no special font or symbol. Um, so then you could write it in a more compact form as the vector y prime equals the matrix A times the vector y. So in order to solve the system, we need to deal with eigenvalues and eigenvectors. And this is going to be a very uh, terse explanation of those. But I think the way I think about it is that when a matrix acts on a vector, it gives you another vector. And I mean, you remember your representing of a vector, think of a vector in two dimensions. It has direction and magnitude, so you can represent it by an arrow with a set length and direction. And in general, when you operate on a vector with a matrix, you'll get a vector pointing in a different direction, right? So let's say we had a vector v, and it was pointed there. And then when I operate on it with the matrix A, I'll get some other vector u, and then maybe u is shorter, and maybe it points over there. So that's usually what happens when a matrix acts on a vector. You get a vector that's a different magnitude in a different direction. But uh, for most matrices, there are special vectors so that when the matrix acts on the vector, it gives you a vector in the same direction, meaning along the same line, um, but the magnitude may change. And that vector is called an eigenvector. And then the way that it changes, the scaling factor, is the eigenvalue. So if it turns into a vector that's twice as long, then the eigenvalue is 2. Now, when we say same direction, this does extend along a line. And so, a vector pointing in the opposite direction um, as a result would still indicate an eigenvector, and then you have a negative eigenvalue, right? So this ends up being kind of a working formula for this definition that the matrix A acts on the eigenvector x. It gives you back uh, a vector that is just a scalar multiple. And then so lambda is used to indicate the eigenvalue, and that's the scalar multiple, and indicate the change in the magnitude. So we're going to want to find these eigenvalues and eigenvectors, and usually there's two eigenvalues for a 2 by 2 matrix, and then again the eigenvector technically it's a full line. Like any vector along that line is an eigenvector, and so we'll just get kind of this direction, and we get to pick. It's almost like just picking like any vector that has that slope, right? Because the line just has a certain slope, and so you'll get to pick two. Usually we pick to avoid fractions and things like that. All right, so using this definition, we're going to rewrite it by subtracting lambda x from both sides and getting ax minus lambda x on the left. And then you sort of factor off the vector x. Now you can't subtract a matrix and a scalar. You can only add and subtract matrices that are the same dimension. So in order for this to still make sense, lambda can't stand alone. It needs to be lambda times a matrix. And so we're using I for the identity matrix. And generally, identity matrix um, is a matrix with ones along the diagonal and then zeros everywhere else. So for this kind of 2 by 2 case, this will be our identity matrix. And if you multiply a vector by this, you just get the same vector back. So that's why it's called the identity matrix. And if we multiply a matrix by a scalar, it just multiplies every element or component in the matrix by that scalar. So the ones, 1 times lambda is lambda, but then the zeros are still 0. 0 times lambda is 0. And so you get lambdas along the diagonal. And so then when you go to do a minus lambda I, you get just minus lambda in the diagonals. All right, let's take a look at example and go through that process. So first we want to rewrite this using the matrix form. So we just take those coefficients and keep them in the same order. And then this tells you that A is that matrix. All right. And then I want to do A minus lambda I. And so I'll just take and subtract lambda there. All right, now what we're actually interested in is the determinant of this matrix. And so you can denote that with determinant. Some people just use vertical bars around this, kind of like absolute value bars. And when we calculate the determinant of a 2 by 2 matrix, we do the product of the diagonals minus the product of the off diagonals. And so the determinant, we would get the -4 minus lambda times 5 minus lambda, and then minus -3 and 6. And what we actually do is we set that determinant equal to 0, and we solve for lambda. So remember, lambda is the eigenvalue. This equation will always come out to be a quadratic equation for this 2 by 2 case. And so then you, again, get that branching into the 3 cases of the nature of the solution set for a quadratic equation. Do you get 2 distinct real values, 1 repeated real value, or the complex conjugate pairs? So that'll all be covered in the methodology. But this process right here gets you started. And so go ahead and try out this example. Oh no, I didn't put I didn't put the matrix in there. You can't actually do it. All right, so let's give you a system. All right. So turn that into y prime equals ay. Determine a, find a minus lambda I, and then find the determinant of a minus lambda I. All right, go ahead and pause the video if you need more time. You should have determined that a is 2, 4, 4, 2. And when we do a minus lambda I, we get 2 minus lambda 4, 4, 2 minus lambda. When we do the determinant of that, we get the 2 minus lambda times 2 minus lambda is 2 minus lambda squared, and then minus 4 times 4 is 16. Now, when you're squaring a difference, you can change the order. And so this is equivalent to lambda minus 2 quantity squared minus 16. And putting the lambda in the front is nicer for when you expand it and solve that quadratic equation. So the correct answer here is A. And then again, you would take that, set it equal to 0, solve for lambdas to get your eigenvalues, and go from there to find the eigenvectors. All right, that's it for the overview. Go on to the methodology now. And thank you so much for watching the videos in this course. And once again, we thank William Trench for the textbook, Elementary Differential Equations with Boundary Value Problems, CC BY and CSA. I'll see you in the next video.